Welcome back. Today we level up from toy examples to a real data set and real questions. Our mission is simple: turn raw rows into answers. By the end of this session, you will be able to 1. Load a real data set into DuckDB inside Colab. 2. Aim your questions with select and where. 3. Rank results with order by. 4. Summarize with group by and the classic functions count, average, minimum, and maximum. And 5. Sanity check results quickly so you trust what you show a manager. We will use the bank marketing dataset where each row is one contact with a client. We will find out who was contacted, how often, and what outcomes we see. Think of it as running a tiny analytics desk from your notebook. Keep your eye on 3 habits. Name only the columns you need. Start with small previews. And write queries you can explain in one sentence. Ready? Let us load the data and ask our first question. First, we install the tools that let us write structured query language inside the notebook. The command installs JupySQL, DuckDB, and the DuckDB engine. Expect a short list of downloads and a successfully installed message. If you see warnings, that's fine as long as the last lines say successfully installed. Next, we import DuckDB and enable the SQL magic. The magic lets a cell run pure structured query language when it starts with the SQL header. Then we create a connection and give it the short alias DuckDB. From now on, when we run a %SQL cell, it will use this connection automatically. To keep an eye on performance, we add the AutoTime extension. After this, each cell prints how long it took to run. That helps us compare queries later. In this chapter, we practice real queries using the UCI bank marketing dataset. Each row is one phone call contact with a client, and the key target is whether the client subscribed to a term deposit. The dataset includes age, job, marital status, education, contact type, campaign counts, and a yes or no outcome. We import a few Python helpers for working with zip files and tables. And then we download the data archive. When it finishes, you should see saved bank.zip with the file size. In this step, we extract the zip, read the bank CSV with pandas using semicolon as the separator, and save a cleaned version with commas. We do this so DuckDB can read it easily in the next step. Here we load the cleaned CSV into DuckDB as a real table named bank. If it succeeds, there is no error and the next select will show real rows. We preview the data with a simple select. You should see columns like age, job, marital, education, contact, campaign, and the outcome Y. If the table is large, the notebook only shows the first 10 rows. Let's request only age, job, and marital and limit to 3 rows. This demonstrates that you should name only what you need and keep previews small. Expect 3 short rows. Same idea, but no limit. You'll see more records. Remember, in analysis notebooks, adding a limit is polite and faster unless you truly need everything. This confirms our table is stable and ready for filtering. Now we filter rows. We ask for contacts where the job is services and the age is over 30. Scan the results to confirm every row meets both rules. This is how you translate business questions into precise conditions. We sort by age from oldest to youngest and show 5 rows. Notice the highest ages at the top. Now we sort the opposite way, youngest first. This is a quick sense check on the range of values. Here we summarize volume by job. Each line is a job category and how many rows it has. Sorting by count is optional, but the raw grouping already tells you which jobs are most common. Next, a 2-column grouping, job and education together. This shows how categories intersect. For example, which jobs most often have a tertiary education. Expect a table with 3 columns, job, education, and count. This returns the total number of rows in the bank table. Use it to sanity check size. This computes the average age across all rows. The result is a single number with decimals. We combine grouping with an average. One row per job with that group's average age. Scan for patterns. Do certain job groups skew older or younger? By this kind of work, we can answer the question. Finally, we grab the maximum and minimum account balance. This quickly reveals outliers. If you see a negative minimum, that usually indicates overdraft or a definition that allows negative balances. For this chapter, we are going to use the Instacart dataset from Kaggle. The Instacart dataset is real grocery shopping behavior. Each order is one shopping trip by a user. Products belong to aisles and departments for easy grouping. We also have an order products table that lists which products were in each order, plus a flag called reordered that tells us if the user bought it before. With these tables, we can answer simple questions like which aisles are most popular, which products get reordered the most, and how many orders each user places. First, we download the data and unzip the file into data folder. Next, we load the CSV files into tables, products, aisles, departments, orders, and order underscore products underscore prior. We sanity check with select star limit 10 on each table and a quick row count on orders. If the previews look right, we are ready to filter with where, sort with order by, and group with group by to get answers fast. Now we join two related tables to enrich our results. Here we connect products to their aisle using an inner join. The result shows each product name next to its aisle name. Inner join keeps only rows that match on the aisle identification in both tables. Scan the first few lines and confirm the aisle label makes sense for each product. Inner join equals overlap only. If a product's aisle ID does not exist, that product will not appear. This join adds department labels. You will see product name, aisle, and department in one row. The matching happens on aisle identification and department identification. Use this pattern when you want readable labels from multiple lookup tables in the same result. Stack inner joins to add more dimensions, and always check the keys you join on. This query brings order headers together with the line items for a single user. Expect to see order identification, user identification, product identification, and add to cart order. It is a classic header to details join. Join on the shared order identification. Filter by user identification to keep the result focused. Now we first pull the user's order lines, then join that result to products to add product names. The output repeats the same orders, but with readable product names attached. This shows how a sub-result can feed a second join for clarity. Build in small steps when results get wide, then enrich with another join for human-friendly labels. This is the compact version of the last two steps. We join orders to order lines, then to products in a single statement. You will see order identification, user identification, product identification, add to cart order, and product name in each row. One query can join multiple tables at once, as long as each join uses the correct key. Now we find the products that both users bought. First, each side builds a list of product identifications for one user. Intersect keeps only the product identifications that appear in both lists. You should see a single column with product identifications, no duplicates. Pick one ID and confirm it appears in both users' orders. If nothing shows up, there is no overlap under these filters. Here we find products that user A bought and user B did not. We start with the list for user A, except removes any product that also appears for user B. You should see a single column of product identifications unique to user A. Spot check one ID. It should be missing from user B's orders. Remember, this is directional. Flip the sides if you want items unique to user B. Now we combine the two product lists and keep every occurrence. Union all stacks the rows from both users into one long list. Duplicates are expected and useful for counting. You should see more rows when the same product appears on both sides. A good follow-up is to group by product identification and count, so you get frequency across both users. If you only need unique products, use union instead of union all. This cell keeps every row from the products table and brings in the aisle name only when the aisle identification matches, so you should see all product rows. And wherever a product's aisle identification has no match, the aisle column will be blank, which proves the left table is fully preserved and lets you spot unmapped products. This cell repeats the left join and then filters where the right side is null, so the result lists only products whose aisle identification did not match any aisle, which is the standard audit pattern to find missing relationships before you build reports. This cell keeps every row from the aisles table and pulls in product identifications when there is a match, so aisles with no products still appear and the product columns are blank for those rows. And if your engine did not support right join, you could swap table order and use a left join to get the same result. This cell returns matched rows plus left-only rows plus right-only rows, and it uses coalesce on the identification, so one aisle identification column is always filled. So in the output, you should notice three cases: matches with both sides filled, products with a blank aisle name, and aisles that have no product. These two short queries are the must-know audits. The first finds products that have no aisle match. The second finds aisles that no product references. Keep these patterns for data quality checks before you build dashboards. Left-only rows reveal broken foreign keys from the left. Right-only rows reveal unreferenced lookups on the right. Remember the mental model. Inner shows the overlap. Left keeps the left and fills what it can. Right keeps the right. Full keeps both. Pick the join that matches the business question and verify keys with a small preview before running larger queries. Subqueries, or nested queries, help us answer a complex question in simple steps. We first ask a small question to get a list or a single number, then we use that result in the main query. We use them to filter by a dynamic list, to compare groups to a benchmark like the overall average, or to add a one-value lookup such as a latest date or a count. They keep queries readable, let us reuse logic without making temporary tables, and help us express business rules directly in one place. This cell simply shows a few rows from the prior order lines, so we know the columns we will use next, including order identification, product identification, add to cart position, and the reordered flag. Confirm the columns look correct and that there are many rows to aggregate. Here we group by product identification and compute the average of the reordered flag to get a per product reorder rate between 0 and 1. Scan the results and note that values closer to 1 mean customers often buy that item again. This cell demonstrates a common mistake by trying to filter on the average inside the where clause, which fails because where filters individual rows before grouping. The takeaway is simple: filter raw rows with where and filter grouped results with having. Use where to filter raw rows before any grouping. It shrinks the data early, which makes queries faster and keeps only the records you care about. Use having to filter after grouping or after you compute aggregates. It keeps or removes whole groups based on results like count, sum, or average. Simple rule: if your condition talks about individual raw values, use where. If your condition talks about an aggregate of a group, use having. This cell repeats the same calculation but moves the condition into the having clause so it filters after grouping. Now the output lists only products whose reorder rate is above the chosen threshold, which is the correct pattern for aggregate filters. This cell selects product identification and name from the products table and keeps only those whose identification appears in a subquery that finds reorder rates above the threshold, so you get a clean list of product names that are frequently reordered. Verify that every ID shown would also be returned by the grouped aggregate from a moment ago. This cell groups the orders table by user identification and counts orders per user, producing one row per user with a simple order count. Look for plausible ranges and keep this result in mind because we will compare users to the overall average next. This cell wraps the per user counts in a subquery and takes the average of those counts, giving a single number that represents the typical number of orders per user. Remember that this is the benchmark we will use to define above average users. Now we list each user with their number of orders. This is a simple baseline, so you can see the full distribution before we filter to above average users. Scan a few rows to confirm the counts look reasonable, then keep this table in mind as our reference. This cell returns only the users whose order count is greater than the overall average computed by a scalar subquery, so the result is a focused list of higher activity users. Confirm that each reported user has a count strictly above the benchmark number. This final cell computes the reorder rate per product and uses a subquery in the having clause to compare each product's rate to the overall average across all products, keeping only those above that global average. The result is a ranked ready list of stronger performers that you can sort or join to names for presentation. In this chapter, we will change tables safely and on purpose. You will learn how to add and drop columns, adjust data types, and create indexes for speed. We will set primary keys to enforce uniqueness and foreign keys to protect relationships between tables. You will see how to rebuild a table the right way, copy data back, and verify constraints with quick tests. By the end, you will know how to evolve a schema, make queries faster, and keep data quality high. We quickly show a few rows from the orders table so you can see the current columns and values. This baseline helps you notice the new column when we add it in the next step. We add a new text column called delivery window to the orders table to store a simple delivery time frame. The success message confirms the change, and a follow-up select should show the new column with empty values. We select a handful of orders again and confirm that delivery window now appears as a column. Values should be empty since we have not populated them yet. We remove the delivery window column to demonstrate how to roll back a schema change. The success message confirms the drop, and the next select should show the original columns again. Now we can see previously added column is deleted. We show the first few product rows so you can see product name as it is now. This makes it easier to verify the type change in the next step. We increase the allowed length for product name by changing its data type to a longer text field. This protects us from truncation when names are long. We select a few product rows again to confirm the table still reads correctly after the type change. The data should look the same, but the column is now more flexible. We run a filter on the large order products prior table by product identification to feel baseline performance. The query returns matching rows and gives us a timing so we can compare after we add an index. We create an index on product identification, so lookups by that column become faster. Indexes trade a bit of space and write cost for much quicker reads. Creating index will take some time. Let's wait till the process finishes. We repeat the same filter by product identification to observe the speed up. The result set is the same, but the runtime should drop noticeably on this big table. Currently, we can see with index the same query took 27.9 milliseconds, but without index it took 90.1 milliseconds. This shows index can help fast search. We count the total rows in order products prior so you appreciate the scale. Large row counts make indexing important for interactive analysis. We reload the table from the original file to simulate a fresh state. This ensures later steps like building composite indexes start from a clean baseline. We count rows for a specific product identification where reordered equals 1. This 2-column filter will feel heavier now. It sets the stage for a composite index. Please remember that it took 125 milliseconds without the composite index. We add a composite index that matches the 2 columns used together in the where clause. This is designed to make that common query shape much faster. Again, creating index take a while. Let's wait till it finishes. We repeat the count with product identification and reordered equals 1 to confirm the composite index helps. The number of rows will match the earlier result, but the run time should be much lower, which is 61.2 milliseconds. We read a few product rows to confirm the table is present. Then we are ready to add a primary key on product identification. We set product identification as the primary key to enforce uniqueness and speed key lookups. The success message means duplicates are now blocked. We try inserting a row that reuses an existing product identification. This should raise a constraint error, which proves the primary key is working and protecting data quality. We select a few rows from orders to confirm it is loaded and ready for a key constraint. We set order identification as the primary key on the orders table, so every order is uniquely identified. This is a standard requirement for clean joins. We display a sample of order products prior to confirm the detailed rows we plan to constrain with foreign keys. We will protect these links next. We temporarily rename the order products train table so we can rebuild it with foreign keys. This staging step preserves the data while we define constraints. We create a fresh order products train table that declares foreign keys to orders and products. This enforces that every line item points to a valid order and a valid product. We copy data from the old table into the new constrained table by joining to orders and products. This naturally excludes any rows with missing parents. Then we drop the old table to finish the migration. We select a few rows from the rebuilt order products train to confirm it loads and looks normal under the new constraints. We query the orders table for an obviously invalid identification to show it returns nothing. This prepares us to test the foreign key rule. We attempt to insert a line item that points to a non-existent order identification. This should fail with a foreign key error, proving the constraint prevents orphan details. A view is a saved query that behaves like a table. We use views to hide long joins, keep logic in one place, and make analysis queries shorter and safer. In this notebook, we focus on views. Stored procedures are programs that run multiple SQL steps on the server, but they are not our focus here. The main idea is repeatable logic you can call by name. The following 4 cells preview aisles, departments, products, and orders tables. We check spelling and column names before we build a view. This cell creates a view that joins products to aisles and departments to produce a single clean table with product identification, product name, aisle name, and department name. We save this logic once so future analysis can read from the view instead of repeating the long join. This cell runs the same 3-table join directly to show that the raw join and the view return the same columns and values. The point is clarity. Use the view for everyday queries and keep the raw join only when you need to tweak the logic. This cell reads directly from the view we just created, so you should see product identification and product name together with aisle and department names in one tidy result, which confirms the view joins are correct and lets you use this single source in later queries without repeating long join clauses. This cell queries the view and filters to rows where the aisle equals T, so you should see product identification and product name with aisle set to T and the correct department name, which confirms the view works as a clean single source for labeled products without repeating any join logic. This cell runs the equivalent 3-table join directly and applies the same T filter on the aisle, so you should see the same rows and columns, product identification, product name, aisle T, and the matching department, proving that the raw join and the view return identical results, with the view preferred for shorter, safer queries. Use the view for everyday analysis to keep notebooks short and consistent. Update the view in one place if names or joins change, and all downstream queries benefit automatically. Today we moved from toy queries to real analysis. We loaded data into DuckDB in Colab, previewed tables, and used select, where, order by, and group by with count, average, minimum, and maximum to answer quick questions. We practiced joins to combine tables, including inner joins for overlap and outer joins to keep unmatched rows. We used subqueries to filter by dynamic lists and to compare groups to an overall average, and we saw the simple rule: use where before grouping and having after grouping. We learned set operations, intersect for both, except for in left not in right, union for unique either, and union all for all rows combined. Finally, we changed tables safely with alter, added indexes for speed, set primary and foreign keys for data quality, and created a view so long joins become one clean source. That is the toolkit you will reuse in every analytics notebook.